Okay, everybody. Let's get started. The lecture today is on a couple of things, but mostly it's on BFS. Okay. So now, what exactly is BFS? How does it work? Okay. So let's say you have uh, a graph like this. This is actually a tree, but I mean same thing. So now I think that you guys are familiar with DFS. If not, then I mean, it's not relevant anyways. But the way breadth search works is it goes from this node to this node, right? Now then it will go this node, then go to this node, right? So notice how it's going only to the neighbors first, and then it goes to the neighbors, and then it goes to the neighbors, and so on and so forth, right? So DFS on the other hand would go till the end of the till it cannot search for any other nodes, right? So it would go like this, and then like this, right? And since there aren't any other nodes over here, it will go back, then go to the next node, and so on and so forth, right? But BFS does not work this way. BFS goes to the neighbors first, right? So now, how is it coded? Okay, now a couple of things which are important in BFS is that so if let's say we have a graph like so, let's say something like this. So now this is not a tree. This is a graph. This why is it a graph? Why it would have been a tree had this edge not been here. Since this edge is here, it's a graph. It's right now I'm just looking at an undirected graph. Undirected graph means that the edges do not have a direction. So now in this undirected graph, this node, let's call this a root node, is connected directly with this, this, and this node, right? So it's connected with these four nodes directly. So in our BFS search, we will first recurse or iterate through these four nodes because these four nodes are directly connected to it. Then it will iterate through all of the nodes which are directly connected to these four nodes, right? So this node, and this node. That's essentially how it works. So it goes from root to neighbors to neighbor, right? And so on and so forth, right? So that's essentially how BFS works. I'll, so this is the code for it. Now it's this code. I mean, I think most of the resources I have are from CP algorithms. It's a very useful site. It has algos for pretty much everything. Um, you can find easier stuff like BFS, DFS, and you can also find more complicated stuff. And I think it's much better than Geeks for Geeks because this is how you write code in a competition, right? You don't have comments in competition. You don't have like the weird uh, class of tree or something, right? You don't write code like that. You write code in a vector of vector, right? Your adjacency list is a vector of vector. So that's essential. So CP algorithms is a lot better than Geeks for Geeks and stuff like that. Okay, but now how is it coded? So DFS is very, I mean, fairly simple to code, right? Because it's just recursion. BFS is a little complicated. So in BFS, we need to use a queue. Now, you may or may not be familiar with what a queue is, but queue is pretty simple. So let me just insert a new slide. So now queue is, I mean, let's say you're at, I mean, this is the basic example, right? Let's say, let's say there are a bunch of people at a shop, and this is like a shop, let's say. So obviously this guy entered first, right? Because he's the most ahead. Then this guy, then this guy, and then this guy. Right. So this is how you enter a queue, right? Now, how do you leave this queue? You leave this guy. This guy will enter the shop first and leave. Then this guy, then this guy, and then this guy, right? So it's so essentially, the one who is entering first is leaving first, right? So the first in, first out, right? I mean, this is how a queue is, right? So whoever enters first will leave first. While in stack, on the other hand, stack is also explained like books, right? So this is the uh, this is the fourth, third, second, first, and this is, and if we are removing a book from this, then this will be removed first, right? So it's first in last out or last in first out, whatever, right? But we're not looking at a stack here. We're looking at a queue. So queue is essentially going to work like this. So whichever is inserted the first will be removed first, right? So let's look at a more algorithmic version of it. So if the queue, I mean, this is how you initialize a queue, right? So now if queue is, let's say, 1, 2, 3, 4, right? Now if you push an element to the queue, let's say you push 5, then the queue will become 1, 2, 3, 4, 5, right? But now if you pop an element, then in a stack we would pop the fifth element, but in a queue we pop the first element, right? That is the only difference between a stack and a queue. Pushing works exactly the same. Pop is just popped from the front of the queue. So over here, okay. So now essentially, now how will a queue help in giving us a BFS code? Well, let's say this. Let's me just number these nodes. 6, 7, 8, 9, and 10. So initially we'll push back the root, right? So your queue. So we'll initially push the root. So our queue will be 1, right? Now then we go into our iteration. So okay, if we look in the code, we push u. Then we have a couple of other things that we need. So in our DFS, we had a visited array. Used is essentially the same thing. So this essentially is only used to track whether a graph has been visited or not. And PFS is the parent. I'll explain that a little later. But then we go into the actual queue iteration. So now we loop through this and we have to keep checking the same thing, right? So first we pop out the element of the queue, right? So the first element would be 1. Our queue would be empty, right? Now then we need to look at all of the neighbors, all of the vertices which are adjacent to our particular node, which is 1. We look at all of the nodes which are adjacent to our 1, which is 2, 3, 4, and 5, and we'll push all of these to the queue, given that these all are not used, right? So if any of these vertices have already been added to the queue, then we cannot add it again, right? So this is this part. So we are just checking if it has been used or not. Now, if it has been used, then we can add these to the queue and put used equals to 1, right? So now our queue would look something like 2, 3, 4, 5, right? So now yeah. So first we have 1, then we have 2, 3, 4, 5, right? Now again we have to pop the first element of the queue, which would be 2. Our queue would be 3, 4, 5. Then we have to look at all of the elements which are adjacent to 2, right? Which is the 6. So our queue would be 3, 4, 5, 6. And now this is the moment where it becomes a BFS and not a DFS. And now you'll notice that why using a queue is required and not using a stack. Right now, had you used a stack now, then we would have gone to 6 next, right? because that is the last element in the queue. But since we are using a queue, we'll go at 3 first, right? So now notice that since we are going at 3 first, then we have to go to 3, then we'll go to 7 and 8, right? But 7 and 8 will also be appended to the end of the queue, right? So it'd be 3, 4, 5, 6, 7, 8. 3 would be popped out, right? But it would go to the end of the queue and it'll go like this, right? But now notice that since it's going to the end of the queue, they are not affecting the ones which are ahead of the queue, right? So 4 and 5 were both ahead of the queue, and therefore, irrespective of any of the elements that you're putting at the end, these guys will always go first, right? So the iteration will always go from 1, then it will go 2, 3, 4, 5, then it will go to neighbors of 2, 3, 4, 5 would be 6, 7, 8, 9, 10. Right? This is how the iteration will always go. So yeah, this is how a queue works, why a queue is used in a BFS. Now, a couple of other things. Had we used a stack, then it would have become a DFS, right? Now, there is unfortunately, I don't think there's a way to do this using recursion. So that is why you don't see BFS as commonly, because DFS has a much shorter code and this has a slightly longer code because it uses queues and stuff. And in general, if you have an option between DFS and BFS, and if you are sure that both of them will work, then it's always better to use DFS. It's almost always better to use DFS because it takes less memory, right? Because DFS is used using recursion, and that will not take any system memory. That will take stack memory. Yeah, so it's generally better to use DFS, but you can also use BFS. Right. So I hope that BFS, the basic functioning of BFS is clear. So we go to the root node, then we go through all of its neighbors, then we go through all of its neighbors, right? And I hope the functioning is clear. So if anybody has any doubt until this point, then uh, you can voice your concern. Otherwise, we'll continue. So does anyone have any doubts up to this point? Okay, cool. So yeah. So now let's go on ahead. So now we are familiar with how BFS basically works, right? Now let's look at some things which are kind of important that people often make mistakes about. So yeah, we'll look at the code in a little more depth now. So now S is our root node, right? We put used equals to true and p equals to -1. Now what is p? Now p is essentially a parent array, right? So parent of x can be equal to y. So what does it mean? So if this is x, then this would be y. That's all it means. So it basically implies that y is the one which we came directly from, right? So x would be the parent of y. Now, of course, there might be a situation like this. So for example, let's say this is y and this is a and b. So now you might ask, what is the parent of what in this case? Uh, I mean, it depends on how BFS runs, right? So if you just look at it, then it might be confusing as to which one you'd consider the parent node. But let's say if the BFS, if if the tree looks like this, right? So now, then how will BFS run? It will go to here, 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 and here, right? So now here in this case it is apparent that parent of y would be a and parent of b would be y, right? There's no other way. I mean, it will have to work like this. So the parent is not a fixed thing. It can change depending on how your DFS is called or how your DFS runs. But for a given BFS call, a parent of some node is always going to be fixed. Okay. So now, why do we use parent, and why is that relevant? So parent, I mean, now we know what DFS is. It's these are all things that are important in why DFS and why BFS, right? So now there's already DFS, so why do we use BFS sometimes, right? So now let's look at a couple of applications. I mean, this is honestly BFS. The biggest application is to find the shortest path, right? I mean, this is by far the biggest application of BFS, right? Because BFS does finding the shortest path in a very simple manner. Finding shortest path is almost inbuilt into how BFS works, and I'll show that to you using an example. So now this is a tree, right? Now, if you want to find the shortest path in a tree, then that's pretty simple, right? Because there's only one path, right? So if this is the root node and this is the node you want to look at, then there is only one path, right? Whose length is 2, right? So if this is y, then there's only one path whose length is 3, right? So finding the shortest path in a tree, you can easily use BFS. I mean, it doesn't matter. The problem occurs if we try to find the shortest path using DFS in a graph, right? So now let me just make one extra change like this. Okay. Now, if this is our root node and this is the node that we are looking at, and we need to find the shortest path between root and node X. Now, using DFS, let's say our DFS run occurs like this. So it goes like this, right? So it goes from root to A to B, B to X, right? So now how will this run? We'll go to root, then we'll go to A, then we'll say, okay, well, the shortest path between root and A has a distance of 1, right? So the shortest path between, let's say, distance is an array which stores the shortest path. So let's say distance of X is the shortest path between root and X, right? So let's just say there's an array which works like this. So shortest path between root and A would be 1, right? If we go through a DFS call, shortest path between root and B would be 2, right? Now, this is incorrect, obviously, because there's a path whose distance is 1. But now, since we are doing a DFS call like this, uh, path, the distance, unfortunately, would still be 2, right? The distance of X would be 3. I mean, this is not correct, right? This is obviously not correct. So now, even if we go to B now, so now then we'll go to distance of B. Then we say, okay, so there's a path whose distance is 1. So let me just make this 1 now. Then, but still, we're not going through all of its roots and updating the value. Right. So even if though we find it as we have found a shorter path to B, we are not updating everything which is below B, right? We are not updating all these values because B has already been visited. Right. So DFS will immediately fail if we are trying to find the shortest path in a graph, right? Uh, and I've noticed people make this mistake a lot. So make sure that you guys don't make this mistake. You can only use DFS if and only if the graph is actually a tree, right? So if there is a graph, if there are cycles and stuff, then you cannot use DFS, right? This is very important. Make sure you guys don't forget it. So you have to use BFS. Now, how does BFS work? Now, BFS by definition will go through all of its neighbors first, and then it will move on, so on and so forth, right? So initially we'll have root in our queue. then we'll populate Q with all of its neighbors, right? So we'll go A, B, C and D, right? A, B, C and D, right? Since all of these are neighbors, right? Now all of these neighbors will update its path like so, right? So we'll update the path of A as the distance between root and x, which obviously the distance between root would be 0, right? Because the distance between root and root would be 0. So this would work like this. So distance of A would be 1, distance of B would be 1, distance of uh, C would be 1, and distance of D would be 1. Right? I mean, this is how DFS works. This is how now, right now, both of them are working this exact same way. The distance of all these values are 1. Distance between root and all these values are 1. Now, how does it work next? Now, so now after this call, then we'll again push all of these elements to the other element. So it will again be now all of its neighbors. So A, B, X, D, then its neighbors E, H, F, G, right? And then after we insert all these values would go away, right? Now, so what would be the distance of E? Distance of E would be 1 plus distance of A, which would be 2. Distance of H, on the other hand, would be 1 plus distance of B, right? Now, in DFS, we have to wait until the whole run is completed to uh, assure that something is correct. In BFS, on the other hand, after the first iteration, after the first time we use all of these numbers, so let's say after, so this is, you can think of iteration as a sort of ordering. So let's say this is the root, and then let's say all of its neighbors, right? So A, B, C, D. Then let's say what are the neighbors of A, B, C, D? E, F, that E, F, G, and H, right? This is how DFS will run, right? So then it will go through neighbors of these values and so on and so forth, right? But now notice that all of these values have a distance of 0. All of these values have a distance of 1. All of these values have a distance of 2. All of these values will have a distance of 3, right? So the way DFS works, the way BFS works is that it follows a level ordering system, right? So if it's running like this, then all of these values are on level 1, all of these values are on level 2, and so on and so forth. And BFS will iterate through all of these elements in this order. So it follows a level ordering system. It goes through this order, right? So that's how BFS works, and that's how you use it to find the shortest path. So yeah, any doubts up to this point? Okay, good. So now we know how DFS is used to find the shortest path, right? We can simply work like this. Now, some people use this sort of implementation, right? Because you're finding the minimum, the smallest path. Both of these values are exactly the same, right? Since you're only going to U once, and whenever you go into U, you are assured that D of U will always be equal to D of V plus 1, right? Since D of V is always the shortest path, right? So both of these implementations are exactly the same. You can use whichever one you want, right? Now, one more thing that you can do is, for example, let's say you know the shortest path, right? Let's say you need to construct the smallest path. right? Now, if you want to construct the smallest path, you also need, along with the distance, you also need a parent variable. All right. So if parent of x would be y, then you know that the DFS must have come from x through y, right? So this is how a parent variable is used. So now notice that, uh, so in this case, v is our variable over here, and u are all of its uh, neighbors, right? So parent of u would be equal to v, right? And then we can say that if we are looking at the BFS call, then it must have gone from u to v through parent of v, and so on and so forth, right? So if we want to find the shortest path between 2 points, then we simply need to go to parent of x, then we need to go parent of x, and so on and so forth, right? Until we get to the root. So this is how you construct the path. This is detailed over here. So we are essentially starting with u until v is not equal to -1, which is just for convenience, we say that. Then we set v equals to parent of u, and then we keep iterating to the path and going up the path, right? And then we can reverse the path to get the actual path that we need in our shortest path, right? So this is how we can find and construct the shortest path in a DFS call. Yeah, so that is pretty much it for finding the shortest path in BFS. Uh, we can also, now let's look at some other applications. So, are you guys familiar with Dijkstra? So, is any one of you familiar with Dijkstra? Okay, I don't think people are familiar with Dijkstra, so maybe I maybe I won't teach this part right now. Okay, so another thing in BFS is you can also have a sort of what we call a multi-source BFS, right? So now let's say we have uh, let's say we have a graph, something like this. It doesn't really matter what the graph is, right? But now let's say we have more than one, right? I mean, this can be possible, right? You can start from multiple points, right? And then you have to go to this, and you need to find the shortest path. Shortest path between a root node and x, right? So now it can take this path, it can take this path, it can take this path, and you need to basically find which is the shortest path. Now, so now the simplest way to do this would probably be to select one root at a time, then find the shortest path from, let's say, root 1 to x, then find the shortest path from root 2 to x, find the shortest path from root 3 to x, then take the minimum of all three. Right now, obviously, this is not ideal since it will uh, take some time, which is too much. So now, BFS, by the way, time complexity would be O n plus m, right? So these are the number of vertices, these are the number of edges, right? Now, this might not be accurate. You might, your implementation might be different, but essentially it's of the order of m, right? So if there are m vertices, generally the order of m. This, if there are n roots, let's say, then this would go to n into m, right? Which is obviously not ideal. So now one thing that we can do, a pretty clever technique, is we can, instead of, so now initially notice how in our BFS, we insert a node and we call it our root node. So now a clever thing that you can do is, instead of inserting one root node, you insert three root nodes, right? So there are three root nodes in the queue right now, then you'll say that the distance of all these three root nodes are all going to be 0. And by the way, 3 is just an example. You can have any number of root nodes. I'm just taking an example of 3. So you have some number of root nodes, and you insert all of these root nodes into our queue, right? And then you can use BFS as usual. But now notice that we'll go in all these directions, right? So we'll go to any node which is a neighbor of any of these root nodes. And since we are going in that way, we can essentially find the shortest path from any root node through X in O of n plus n, right? So this is known as multi-source BFS. This is used sometimes when there are multiple roots. It's a useful technique for you to know. Okay, now now this is bipartiteness. Is yeah. So this okay now. What is a bipartite graph, right? So now let's look at the same example. Now a bipartite graph is essentially if you can convert the graph into two sets such that both of these sets are uh, essentially not interacting with another. Right? So none of the edges in the first set should be adjacent to any of the edges in the second set. So now how can we do that? Now let's say squares and circles. Right? Now notice that none of these circles are adjacent to any other circle. Right? And none of the squares are adjacent to any other squares. Right? A construction like this is known as a bipartite graph. Now, not all graphs have a construction like this. So for example, let's say if your graph is something like this, uh, so you okay, so this graph actually has a bipartite solution because it has an even cycle, right? But now let's say a graph has an odd cycle. So you can see that there's no way to have our edges in circles and squares such that any two circles are not adjacent to each other, right? So you always have two circles which are adjacent to each other, or two squares which are adjacent to each other, right? So you can't have a bipartite graph in all cases. When can you have a bipartite graph? You can definitely have a bipartite graph if there is a tree. If there are even cycles, then there's still a possibility of bipartite graph, but it becomes a little complicated, right? But how does a bipartite? So how do you actually write the code for bipartite graph? You can honestly use the same code for finding a bipartite uh, connection, I guess. So now notice that initially distance of S was equal to 1, and then we add 1, right? So if we just take XOR with 1, then what happens? So now 0 XOR 0 uh, is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0, right? So now notice these things. So whenever you XOR 0 with 1, you get 1. Whenever you XOR 1 with 0, you get 0, right? So essentially, it inverts the bit, right? You can also use it essentially works like this, right? Now, not function. This is a little problematic. I'll be honest. Sometimes it works very badly. So 0 0 0. Not of this would be 1 1 1 1 1. Right? I mean, this is not what you want. You want it to be. You want only one bit to be zeroed, but it might zero everything. So not is generally not used as commonly. Uh, in this case, it can probably be used, but still, XOR is a little easier. So now, what is it doing? I mean, it's essentially just saying that okay, if my parent was a 0, then I'll be a 1, right? And if this guy's parent is 1, then this guy becomes a 0, right? That's pretty much it for bipartiteness. I mean, it's pretty simple. You just it's just a way to convert it into a graph such that none of the two edges have the same color. So if you color it 1, then you need to color all of its descendants 0, and then you had to color all of its descendants 1, right? Now, how do you check if a graph is bipartite? Well, you can just make this ordering, right? It's simple enough to make. And then if any of these orderings, so if you have made an ordering, and let's say it looks like 0, 1, 1, 0, and like this. So now, while you are making this ordering, you'll notice that there is no way to make this guy a 1, right? Because it's already a 0. So if you ever find such a case where after making the bipartiteness, if there are any two connected, any two edges any two nodes which are connected by an edge, if any of these two values has the same color, then the graph is not bipartite, right? So now this is how you check if a graph is bipartite and how you make a bipartite connection. Now let's look at cycle detection algorithms. Now cycle detection algorithms, you can BFS not generally used. BFS is more commonly used, and I think if you think about it, BFS you can't use in a lot of these cycle detection algorithms. Now, the way cycle detection algorithm works is fairly simple, and it can get honestly pretty complicated. So now, I'm going to look at a simple undirected graph, right? This is very important. Undirected graphs and directed graphs have a different way of finding cycles. It's a little complicated when you're dealing with an undirected graph. So if your graph looks something like this, then finding a cycle not that difficult. You can just do a DFS run. So let's say it goes like this, 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 that, and then it will go like this, and then it will go like this, right? So now notice that once it's going from here to here, you'll notice that it is going through an edge which has already been visited, right? So if any of the edge it's going to has already been visited, that means there must be cycle, right? Because you're going through an edge, and the edge you notice that there's already a way to go through an edge, right? So there essentially a way that you're going, and there's some other way. So there are two ways, and therefore there's a cycle, right? So so essentially, so if so now notice that one sort of caveat there is that you can also go through this edge. This edge has been visited, but it's a parent of this edge, right? I mean, you have visited it like this, right? There's no other way to visit it. So now you don't have to look at the parent, and you have to look at any other element which is not the parent, right? And if it goes to any element which is not the parent, and that element has already been visited, then there is a cycle. Right now, the code is not that complicated, so we just not like normal DFS. We set visited equal to true. If the edge is a parent, then we won't iterate through it. Obviously, we want to go back to the parent, right? And if it's visited, that means a cycle must have existed. So we know that the cycle must have started at U and ended at V, right? So let's say if this is U and V. So if we go through, let's say this is U, this is V. So if we find a cycle like this, then we can say that there must be a cycle between U and V, right? So we just put cycle start, cycle end, and then we can set that cycle is true, right? And then we set parent of now then the parent function again works like normal DFS, right? So if this is X, then this would be parent of X, right? If this is Y, then X would be parent of Y. Then we just keep setting this value, and then we keep DFSing. right? So now DFS in an undirected graph to find the cycle is not that complicated. We just DFS as usual. We just make sure that we are having our parent, right? So if we have a parent of every node and a node has already been visited, then there must have been a cycle. Now, why do we have a parent? Well, we use a parent to form the cycle, right? So now we have a cycle. Now we need to form the cycle, right? Uh, I yeah. So how does the cycle? How do we form a cycle? I mean, we have again. So we know that there's a cycle between U and B. We can simply go from B to U through its patterns, right? So if the cycle, if we know that the cycle starts at U and ends at B, then we can go to U, the parent of U, the parent of U, so on until we reach V, right? And this is our cycle. This is how you can form a cycle and how you can print the cycle. Now, this is essentially a code to print the cycle. It says the pretty much same thing. If we do not find a cycle, then it's acyclic. Then we can set the start value, keep iterating through its parent value until it's not equal to the start value, keep pushing back, then reverse the cycle. Right? This is how it works in a undirected tree. Not super complicated, but not that simple if you've never heard of it. Now, why is it different in undirected tree? Why is it now this we are looking in the case of a directed graph rather. Now, the only difference between a directed graph and an undirected graph is the existence of back edges. Right. So now notice that in this case, this is a cycle, right? You go from here to here, here to here, here to here, here to here, right? Pretty obvious that's a cycle. This is not a cycle, right? You go from here to here, here to here, here to here, here to here, right? This is not a cycle, right? But if we go in our same method like we did in our the undirected graph, then how will this work? So it will go from here to here, cool. It will go from here to here, cool. Then it will go to our DFS. So now there are no other edges that it can go. It will backtrack, go from here, go to here. Then it will notice that this element has already been visited, right? Since this element has already been visited, it will say that a graph is exist. But we can see that a graph does not exist, right? Now, had this been an undirected graph, this would have been just four edges, and it would have been a cycle, right? We can go here, 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 here. But since it's a directed graph, you can see that clearly, yes, there is a way to get through this point using two different paths, but it does not constitute a cycle, right? So now, why does this happen? You can think of it happening if you look at this case, then it should be a little apparent. So now in this, if we now there's a cycle here. So how will the DFS run look like this? So it will go here, 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 here. Now notice that this element has already been visited, and there is a cycle. Now what is the difference between both of these runs? Uh, in this run, this element you have already backtracked from this element, right? So that means that you have gone through this element, you have gone through any of the elements which are connected through it, you have gone through all of those nodes, and you have moved on, right? So you have visited all of these nodes, and then you have moved on, right? So you have backtracked. So you have already dealt with any node which is connecting this node, right? So if let's say a cycle had existed, which included this node, then we would have already found it. right? Because you'll only backtrack when you have visited everything. If you have not visited everything, then you'll still be in one of these nodes and you would not have backtracked. But the very definition of your backtracking means that you have already visited all of the nodes. Now, if you have visited all of the nodes, then even if you encounter this node again, it does not mean that there's a cycle. It just means that there's another way to get to this node, right? And in this case, notice that we'll only backtrack to the point one once you have uh, dealt with every edge which comes in its subtree. Since we have not dealt with every edge in its subtree yet, we have not backtracked yet. Since we have not backtracked, there is still a cycle, right? So it's a little more complicated, but instead of two colors, we have three colors. Uh, 0 would say unvisited, 1 would be visited but not backtracked. You can think of, instead of thinking of backtrack, you can also think of it being in the recursion stack, right? So now notice that there is going to be a recursion stack. So if a graph looks like this, A, B, C, D, then you can think of it as a stack. So it will go A, then B, then C, pop out C, go go become A, B, D, pop out D, pop out A, uh, then go to AE, pop out E, pop out A. Right? I mean, this is how you can think of recursion in a stack format. So you can either think of it as visited. So now notice whenever we backtrack from an element, that element gets popped from the stack. So if the element is if the color is 1, then we can say that the element has been visited, but it is still existing in the recursion stack, right? We have not backtracked it. If we say that 2, then we can essentially think of this element as done. It does not exist in the recursion stack. Backtracking is done, right? So now if the backtracking is done and if it does not exist in the recursion stack, if there's a cycle, then we would have already found it and we need not look for it again, right? So now we can, after dividing uh, the graph into three different paths: unvisited, visited, not backtracked, and visited and backtracked. After dividing it into these paths, it should be apparent that only if you visit a number whose color is 1 there is a cycle, right? Because that element is still in the recursion stack, right? So so you can see that the same thing in code. So you make all of the elements 1, which means that it has been visited, not yet backtracked. If color is 0, then it's just unvisited. Then you just DFS. If color is 1, that means you have found a cycle. We do the cycle start, cycle end in the same process. We use parent in the same process. It's just to construct the cycle, parent of u, parent of u, and so on and so forth. And then after all of these, we set color equals to u. Right? So after we have visited so this will constitute visiting all of its neighbors, all of its children, all of these values, and recursion stack. So essentially, the entire subtree we'll find and recurse through, and then only then we'll set color equals to 2. Right? Once we set color equals to 2, that we know that it has been visited and has been backtracked. We do not need to go into this element again, right? And this is just how you find the cycle. So this is how you find the cycle. Exact same thing that we did in our last example. Not that complicated. You notice that since it's an acyclic tree, you do it like this since it might be unconnected. Had it been connected, you could have just DFS through one point, but since it's unconnected, you have to DFS through every point and check it as a visitor now. Yeah. So that is it for cycle detection algorithm. Since we have a little time, I'll just give you a brief intro as to what this is, and then we look at one or two questions. So this is known as 01 BFS. So you can, so 01 BFS essentially works in this way. So you can set, so now let's say we are dealing with a directed graph. Let's say we are dealing with a directed weighted graph, right? Now, if we are dealing with a directed weighted graph, then the way that you solve this is using Dijkstra. Now, what is that Dijkstra? How do you exactly use it? That will, I mean, you can reach into it, or it will probably be taught some other time. I'm not going to tell you what Dijkstra is, but you can just think about it, and that it is used in a, it is used to find the shortest path in a directed unweighted graph, a directed weighted graph. Sorry. Now, if you want to find the shortest path in uh, weighted graph, then we can use Dijkstra. But now, let's say that this is a simpler case. So now, let's say the weights can only be 0 or 1, right? Nothing else. So if the weights are only 0 and 1, then you can use BFS. And it's called 01 BFS. Now, how does it work? Uh, so you can think of 1 as infinity, right? And 0 is 0. So now infinity is always greater than 0, right? So you can think of it as your normal Dijkstra, but instead of using a priority queue, you can just use a queue. And you notice that whenever you're putting a 1, it will always be put to the front of the queue. And whenever you put a 0, it's always put to the back of the queue. Right? So this is a way to use Dijkstra, to use BFS to simplify Dijkstra. It's fine if you don't understand it. I think it will be more clear once you're taught about Dijkstra. But just remember that you can convert, instead of finding the shortest path, instead of finding the shortest weight, you can just convert Dijkstra into either putting a number in the front or at the back. Right? I mean, it's fine if you don't understand it. It's just another way to look at Dijkstra using BFS. So just another application. Are there any doubts up to this point? If not, then we'll look at a couple of questions. So if there are any doubts, feel free to speak up. I'll give you a few moments while I have a drink of water. Otherwise, we'll get started with looking at a problem. So if there are any questions, please speak up. Okay. Yeah, Max. So I don't think there are any doubts. So now let's look at a couple of questions. So now the I'm just going to look So, by the way, I hope that you guys are keeping up with code forces. I mean, you guys might have your internships this summer, or you'll be preparing for it for the next year. But doing code forces is pretty important. I think there's a competition today, so make sure you guys do it. I think it's, I don't know, at 8 or something. So make sure you guys do that competition. Yeah. So now let's look at a couple of problems. So okay, not this one. I mean, this is a 2500 problem. Right? Yeah. Okay. So now, uh, I request everyone to read this problem. Uh, I'll give you a couple of minutes, then I'll explain the solution. So yeah, everybody, please read the problem. And if you have any doubts about the problem, feel free to ask me. Okay, so I hope that everybody has read the problem. So now let me just explain how I'm going to approach to solve the problem. So now this problem is based on bipartite graphs. So yeah, so it's essentially given that first of all it's given the definition of bipartite graph, and then then you are asked to essentially add some edges such that the graph remains bipartite. Right, so you just need to find what are the maximum edges that you can add such that the graph keeps its bipartiteness property. Right. So now we already know when a graph is bipartite. So already learned about that. We know how to find bipartiteness. But now how do we find what is the maximum number of edges we can put? So now notice that the graph is a connected acyclic graph, right? So it's not a tree, it's a connected acyclic graph. So if it's acyclic and if it's connected, I mean, I think that's a tree. Yeah, okay. So it's just a tree. So yeah, so now let's say a tree looks like this. Then how do you make this graph bipartite? Well, you can set each of these values as 1 or 0. So if it's 1, then these would be 0, and then these would be 1, right? So notice how it goes 0, 1, 0, 0, 1, 0, so on and so forth. Yeah. So now we need to add edges such that the graph still remains bipartite. Okay. So now how how are you going to do that? Now notice that we cannot connect these two edges, right? Since this would be an example of multiple edges, right? We can only have one edge connecting two different numbers. So now let's try connecting 0 and 0. Now notice the moment you connect 0 and 0, the bipartiteness property is broken, right? And there is in fact no way to rectify this bipartiteness since we have formed a odd cycle, right? Now let's try the same thing with over here. Again, we notice that we have formed a 1, 2, 3, 4, 5 odd cycle. We know that that cannot be possible. Over here, we found a 3 cycle now, right? So obviously, apparent that we should not connect two edges who are connected by the same color. Okay, so now what happens if we connect two edges with a different color, right? So now, now notice we cannot connect 0 and 1 since that would create multiple edges. But if we connecting these two values, then it creates a cycle, but the number of elements in the cycle is 4, right? So it creates an even cycle, and we already know that that is acceptable to have a bipartite graph, and you can notice that this graph still remains bipartite. 0 is still connected to 1, 1 is still connected to 0, 0 is still connected to 1. Right, so this essentially means that you can connect two points which are 0, and then you can connect it to another point which is 1. Right, so now let's say the number of 0 colors is x, and the number of 1 colors is y, right? Then you can connect each of the 0 component with each of the 1 component, right? So you can have x into y total edges, right? I mean, there's a simple permutation combination thing, right? So if there are x ones and if there are y zeros, then you can connect each one with any of the other ones, and the total number of ways you can connect would be x1, right? But now notice that you cannot connect these two values, right? You cannot connect these two values. Even though they are 0, 1, you cannot connect them because that would create multiple edges, right? So out of these total edges, we can not connect all of these values because some of these values are already been connected, right? So how many values have already been connected? Well, n minus 1, right? So because there are n nodes, n minus 1 edges. So the answer just is xy minus n minus 1. That is the entire solution, right? You just need to convert it into a bipartite graph. You need to find how many elements are x and how many numbers are connected 0. Then you just multiply both of these values and subtract the number of edges from these numbers. That is it. That is how this bipartite problem is solved. So does anybody have any doubts with this problem? If not, then we'll move on to the next one. So does anyone have any doubts regarding this one? Okay, so now let's look at the second problem that I've chosen. Uh, it's right here. So again, read the problem. If you have any doubts, then uh, voice your thoughts. Okay, does and everybody understand the problem? Are there any doubts? Okay, so now in this problem, uh, we have a parallelepiped. I mean, it's just a cuboid, right? So we essentially have a cuboid with a bunch of layers, and we have some empty squares and some obstacles. And then we need to find, and some of the squares are empty and some are not. And then we need to essentially find uh, how what is the amount of time it will take to fill the plate. right? I mean, if you can visualize this, then it would be a little easier. So I don't know if my drawing would be able to justify it, but you can think of it as a cuboid. Then we have a couple of layers. Then you can layers like that, that. Okay, so now we can have some holes over here, right? So now let's say these points are holes, right? So now let's say this also hole, this also hole, this also hole, this also hole. So if there are a bunch of holes like these, then I notice that the water will go in all of these holes, right? And it won't overfill. So once it has filled all these holes, at that moment it will overfill. Right. So now let's just look at the same case in a 2D fashion. So now let's say the water can, I don't know, spread. Right. So instead of thinking, let's just forget about gravity for a moment and think that the water can spread horizontally in any of the four directions. Right. So now let's say this is our tap source and this is an obstacle. Let's say this is an obstacle. This is an obstacle. This is an obstacle. This is an obstacle. Right. And this is our tap source. Right. Now we can say that the water can spread in any of the four cardinal directions. Right. So now if we are spreading the water in any four cardinal directions, we need to find the smallest amount of time in which we can reach all of these points. Right. Now notice that a couple of good things to keep in mind. A grid can always be represented as a graph. Right. So if you are at this point, then you can visit these 4 points. Right. So you can think of this graph as a node with four edges, right? And therefore you can completely convert a grid into a graph, right? So you can convert a grid into a graph such that there are a bunch of nodes and each nodes has four edges, right? Or in case of a 3D figure, each node can have six edges, right? Because there is also a top and a bottom component. So you can convert it into a graph. Now we need to find the shortest time to essentially reach every point, right? So essentially we need to find the maximum of the minimum possible distance to x, right? And we need to find the maximum of through all of these x's, right? So essentially, so now after we convert this into a graph and we think about the graph in this way, then it it should be obvious that we need to use the BFS, right? So how do we use BFS? We just start at this point, then we go to all of its neighbors, go to the neighbor of neighbors, then go to all of the points, then we iterate to all of the points, and then we need to find the maximum of the distance between that point and our node. Notice that this distance will always be the minimum distance since we are dealing with the DFS, right? So now if we look at the complete problem, then it just becomes that we start at this point, then we need to run a DFS in all six directions, right? So what would the six directions be? It would be top, down, and then the four cardinal directions, north, south, east, west. Right? So we have to run BFS in all of these points. Then we need to go through all of these points, and then we need to find what was the minimum possible distance from that point through the root node. Then we need to take the maximum of all these values, and that is our answer. Right? So are there any doubts about this question? I think this is the last question. So if there are not any doubts, then we can conclude the session. So if you have any doubts about this question or about the session as a whole, so feel free to raise your doubts. Okay, if there are not any doubts, I think we can end the session unless. If there are any doubts regarding the session or I mean anything in general, you feel free to uh, speak up. Otherwise, we can end the session. Okay, cool. So I think we can end the session now. So unless anybody Anubhav, Manak, you have anything to say?
Okay, I guess we can end the session. Let's stop the recording.
Yeah, cool.